In this module, we will look at how we find the pH of both strong and weak acid solutions. Our objective in this unit is to calculate the pH of both strong and weak acid solutions because we have different procedures for each. Finding the H+ concentration of a strong acid is fairly easy, so finding the pH of that same solution is a straightforward process. When we look at a strong acid, we know that it is a strong electrolyte, meaning it ionizes completely. HCl goes to H+ and Cl-. If we have a solution that is 0.050 molar HCl, as in that's the concentration that we measured, then we can know that the complete dissociation or complete ionization will result in all of that HCl being converted into H+ and Cl- ions. So if we have a complete dissociation and we know the initial concentration of HCl, then we can also find the final concentration of H+ because it will be the same as the initial. Therefore, our H+ is going to be equal to 0.050 molar. Once we know the H+ concentration, finding the pH is easy. pH equals negative log of the H+ concentration. So in this case, pH is equal to negative log of 0.050 molar, and our pH will be equal to 1.30. Note that I have 2 sig figs in my original concentration, so I have 2 decimal places in my answer. Finding the H+ concentration of a weak acid is a little bit different. Because we don't get a complete dissociation or ionization, we have to figure out what fraction of our acid dissociates into the ions. If we look at our reaction, we have HA yields H+ plus A-, and this is an equilibrium process. And if you're not sure if something is a weak or strong acid, the presence of that equilibrium arrow indicates that it is in fact a weak acid. If we look at our initial concentration of HIA, we see that it is not equal to the final H+ concentration as it was for the strong acid, because not all of our HA is divided or dissociated into the H+ and A-. We have to look at Ka, the acid dissociation or ionization constant for the acid, and remember this is just an equilibrium constant for the acid. So our procedure is going to be much more like what we did in the previous unit talking about equilibrium. We're going to use an ice table to solve for that unknown concentration. Let's look at an example. What is the pH of a 0.200 molar solution of HF? And we're given that the Ka value is equal to 3.5 times 10 to the minus 4. Here we have HF, aqueous phase, going to H+ plus F-. I set up my ice table, remember initial, change, and equilibrium. I know my initial concentration of HF is 0.200 molar because that's what was given in the problem. I know my initial concentrations of H+ and F- are 0 because we haven't had any dissociation to occur initially. Then I look at my change row. I'm going to lose some amount of HF, and I'm going to gain the same amount of H+ and F- because of the coefficients. It's all a 1 to 1 to 1 ratio. And then I see that for my equilibrium row, I have 0.20 minus X, X, and X. Now I can set up my law of mass action, plug in my terms from the equilibrium row, and solve for my concentration. So let's look at that, how we would do that. So here we have H+ and F- are both equal to X, so I can say that's equal to X squared, and the HF is going to be 0.200 minus X on the bottom equal to 3.5 times 10 to the minus 4. Just as we did in the earlier equilibrium problems, we want to make the simplifying assumption that X is much, much less than 0.200. Given the small value of Ka, this is probably a reasonable assumption, but we would still need to do the calculation just to make sure. So now we've got our X is less than 0.20. We've simplified our expression. So let's rewrite what we have left. Now I've lost the minus x because we've simplified. Now I can multiply both sides by 0.200. And when I do that, I end up with 7.0 times 10 to the minus fifth equals x squared. I can take the square root of that number and find that x equals 8.4 times 10 to the minus third. And that will be equal to my H plus concentration. From that, if we wanted, we could find the pH value, or we could go on to find the OH minus concentration using what we know about Kw and finding the pOH value. Another way of looking at the acid strength is to look at the percent ionization of weak acids. What we can look at is the H3O plus concentration at equilibrium, or, remembering that's the same thing we've been calling the H plus concentration, those mean exactly the same thing, divided by the initial HA concentration and multiplying by 100. The bigger the value of the percent ionization, the stronger the acid, and vice versa. The smaller the percent ionization, the weaker the acid. Let's look at an example of how we can use this information to figure out the pH of the solution. Here we have HA in equilibrium with H plus and A minus. It's a 0.350 molar weak acid that is 13.2% ionized, and we want to find the pH of the solution. We have our percent ionization is equal to H plus at equilibrium over our HA initial times 100. I can plug in the values I know. 13.2% equals H plus at equilibrium over 0.350 initially times 100. Now I can rearrange and solve for my H plus concentration at equilibrium and find that it is 0.0462. Now that gives me the concentration. It does not yet give me the pH value. I have to take the negative log of that number to find the pH value, which is 1.335. We have 3 digits in our decimal place in the mantissa of the log because we have 3 significant figures in our concentration. When I look at a mixture of strong and weak acids, I have a couple of things to consider. First of all, the strong acid will completely dissociate or ionize because I go from HCl to producing H plus and Cl minus, and all of my HCl will dissociate. So I have a fairly large concentration of H plus present. When I look at the HA, if I just had the weak acid by itself, I would see the formation of some H plus and some A minus. This number, even by itself, is going to be a small number. So compared to this H plus that I get from the acid. However, because the weak acid process is an equilibrium process, okay, we've got our equilibrium arrow there, it's an equilibrium process, what we're going to see is that the presence of the H plus from the strong acid ionization will actually drive the equilibrium towards the left for the weak acid. And as a result, the small amount of H plus I actually had present from dissociation of the HA will actually get smaller in this mixture with a strong acid. And so what I find is that the primary H plus source will be the strong acid, and the amount of H plus produced from that weak acid is so small that it becomes insignificant and I can ignore it. Now, if I'm looking at a mixture of 2 or more weak acids, I have multiple reactions going on, and just like I did with the strong and weak acids, I'm going to find the strongest of those acids. If their values are fairly different from one another, say we have Ka values of 10 to the minus 3, 10 to the minus 5th, and 10 to the minus 9th, those Ka values are far enough separated from one another that I really only have to look at the one that has the Ka of 10 to the minus 3, and I will do all my calculations as if that were the only one present. Now I want to look at an example. Which one of the following is associated with the strongest acid? Now note these all have Ka values, so they are all weak acids, so we're asking which one is the strongest weak acid of these 4. Hopefully you answered the first one, 1.9 times 10 to the minus 4th. This is the largest of the Ka values for these 4. Therefore, it will be the strongest acid of these. We've talked a lot about acids, both strong and weak. In the next module, what we're going to look at is bases.